In this EzEd video lecture, we will learn modulation techniques, wherein we will learn about block diagram of modulation, types of modulations, and different analog modulations as amplitude, modulation, frequency modulation, and phase modulation. Consider a situation in which a person has to send a parcel from place A to place B, which is very far from A. Hence, that person will first contact a courier company. The courier company will send the parcel via a bus from A to B. At place B, someone from the courier company will receive that parcel and deliver it to the destination. Thus, the parcel becomes a baseband signal. The bus becomes a carrier, and the courier company becomes the transmitter and the receiver. We know that the information signal to be transmitted can be of any form such as data, music, video, etc. But before transmission, it is first converted into its equivalent electrical form. The electrical equivalent of the original signal is called as the baseband signal. Every electrical signal possesses basic characteristics such as amplitude, frequency, and phase. We need to change the characteristics of the signal to make it more appropriate for transmission. The process of varying any of the three characteristics as the amplitude, frequency, or phase of a carrier signal is called as modulation. Hey, it's time to concentrate now. Modulation is required for the following reasons: reduction in the height of an antenna, avoids the mixing of signals, makes multiplexing possible, increases the range of communication. Let's see the block diagram of modulation now. We have two inputs such as modulating signal and the carrier signal, and at the output we get a modulated signal. Modulating signal is nothing but the information signal. This modulating signal is primarily of two forms, as analog signal such as music, image, etc., and digital signal such as computer data. Based on this, modulation is divided into two types, such as analog modulation and digital modulation. Analog modulation is further divided into amplitude modulation, frequency modulation, and phase modulation, whereas digital modulation is further divided into pulse amplitude modulation, pulse width modulation, and pulse code modulation. We will only focus on analog modulation. Let's see the modulation techniques one by one, starting with amplitude modulation. Amplitude modulation is the process of changing the amplitude of the high frequency carrier signal with respect to the instantaneous value of the modulating signal. Shown in the diagram below, first is the modulating signal, that is the information signal. Second is the high frequency carrier signal. And third signal is the modulated signal. If we concentrate on the third signal, then after joining every peak of the modulated signal, we get the information signal shown below by dotted lines. Thus, in amplitude modulation, the amplitude of the carrier changes and the frequency and the phase of the carrier signal remains constant. That is, the information is contained in the amplitude of the carrier signal. Now let's analyze the AM signal mathematically. Assuming the modulating signal is to be sinusoidal, it can be represented as EM equals EM into cos omega m into t, where small em equals instantaneous amplitude of modulating signal. EM equals peak amplitude. Omega m equals 2 pi FM, and FM equals frequency of modulating signal. Similarly, the carrier signal is given by equation small ec equals cos omega c into t, where ec equals peak carrier amplitude and fc equals carrier frequency. The amplitude modulated wave is given as EAM equals A into cos 2 pi fct, where A equals instantaneous amplitude of an envelope. Hence, we can represent this instantaneous value as A equals EC plus EM. We substitute the value of EM in this equation to get the expression for A. Substituting the value of A in equation of AM wave, we get the equation for amplitude modulated wave. The ratio of amplitudes of the modulating signal to the carrier signal is called as modulation index M, and is equal to Em upon Ec. Thus the AM wave is represented as shown. Now let us see the frequency spectrum of the AM wave. Frequency spectrum is a graph of amplitude on y-axis and frequency on x-axis. Consider the equation of the AM wave. On simplifying, using trigonometric identity, 2 cos A cos B equals cos A plus B plus cos A minus B. Thus, we get the equation. The equation of the AM wave thus becomes EAM equals EC cos omega CT plus MEC by 2 into cos omega C plus omega MT plus MEC by 2 into cos omega C minus omega MT. The first term is a carrier signal. The second term is the upper side band. And the third term is the lower side band. Thus we get the frequency spectrum of the AM wave as shown with the carrier and the two side bands. The bandwidth of the AM signal is obtained by the subtraction of the lowest frequency component from the highest frequency component. It comes out to be equal to 2 FM. Consider an example now. The modulating signal 20 cos 2 pi into 10 raised to 3t is used to modulate a carrier signal 40 cos 2 pi into 10 raised to 4t. Find the modulation index percentage modulation, frequencies of sideband components and their amplitudes. What is the bandwidth of the modulated signal? We have Em equals 20 cos 2 pi into 10 raised to 3t. Ec equals 40 cos 2 pi into 10 raised to 4t. We need to find modulation index M, percentage modulation, frequency of upper side band and frequency of lower side band. For that, we use standard equations of modulating signal and carrier signal, and the formula M equals Em upon Ec and bandwidth is equal to 2 into Fm. The standard equation for modulating signal is Em equals Em cos omega Mt. The equation of the modulating signal is Em equals 20 cos 2 pi into 10 raised to 2t. On comparing, we get Em equals 20, omega equals 2 pi into 10 raised to 2, thus Fm equals 1000 Hz. The standard equation of carrier signal is Ec equals Ec cos omega Ct, and the given equation is Ec equals 40 cos 2 pi into 10 raised to 4t. On comparing the two equations, we get Ec equals 20, omega m equals 2 pi into 10 raised to 4 into t. Thus Fc equals 10,000 Hz equals 10 kHz. The modulation index is calculated as ratio of Em to Ec and comes out to be equal to 0.5. Thus percentage modulation becomes 50%. The upper side band frequency equals carrier frequency plus modulating frequency equals 11 kHz, and lower side band frequency equals carrier frequency minus modulating signal frequency equals 9 kHz. The amplitudes of each side bands are MEC by 2 equal to 10 volts, and the bandwidth required is 2 into Fm equals 2 kHz. Let's move on to the AM transmitter now. But first, we will learn about the oscillator and power amplifier. Oscillator is a circuit which generates oscillation, that is, it generates different sinusoidal waveforms. Crystal oscillator is the type of oscillators primarily used in AM transmitters. Power amplifiers are primarily used to increase the signal strength before its transmission. We have three major power amplifiers as Class A, Class B and Class C power amplifier, which differ in their efficiency. All these amplifiers are basically bipolar junction transistors. In Class A amplifier, the collector current flows for the entire input signal. As this amplifier uses the entire input signal, its efficiency is low. In Class B amplifier, the collector current flows only for half of the input signal. As this amplifier makes use of only 50% of the input and produces the output, we get around 78 to 79% of efficiency. In Class C amplifier, the collector current flows for less than half of the input signal. That is, It gives efficiency of around 90%. Now, we can move on to learn AM transmitters, which are of two types: high-level modulated transmitter and low-level modulated transmitter. We will first see a high-level modulated transmitter. Its block diagram is as shown. Here, the crystal oscillator generates the carrier signal. It is then amplified by Class C power amplifier. The modulating signal is also amplified to a higher power level before modulation. The modulation takes place in the last Class C power amplifier. The modulated output is AM wave, which is transmitted directly. The advantage of high-level modulation is its high efficiency due to the use of Class C power amplifiers. The disadvantage is large power amplifier is needed to raise the modulating signal to the desired power level. The next transmitter is low-level modulated transmitter. Its block diagram is as shown. In low-level modulating transmitter, also, the carrier signal is generated by RF oscillator. The modulator is separate block in this case. The modulating signal is amplified using Class A amplifier. At the output of the modulator, we get the modulated wave. This modulated wave is then passed through a series of linear amplifiers to raise its power level. For low-level transmitter, high power AF is not required for the modulated signal. Thus, its design is much simpler than the higher level transmitter. Now let's see the advantages and disadvantages and applications of amplitude modulation. Advantages of AM. AM transmitters are less complex. AM receivers are simple. Detection is easy. AM waves can travel long distance. Low bandwidth. Disadvantages of AM. Power wastage takes place. AM gets affected due to noise. AM needs larger bandwidth. Applications of AM: radio broadcasting, picture transmission in TV system.
Hey, it's time to concentrate now.
Let's study the second type of modulation technique, frequency modulation. In amplitude modulation, the amplitude of the carrier changes and the frequency and the phase remains constant. In frequency modulation, the frequency of the carrier signal varies, whereas the amplitude and the phase remains constant. We know that the frequency and the time period are reciprocals of each other. Thus, when the time period of a signal is minimum, we get maximum frequency and vice versa. We can see above, as the amplitude or the information content of a modulating signal increases, the frequency of a carrier signal also increases. Its time period decreases, hence the signal gets compressed. And as the amplitude of a modulating signal decreases, the frequency of a carrier signal also decreases. Hence, its time period increases and the carrier signal expands. Now, let's see the concept of frequency deviation. The amount by which the carrier frequency varies from its unmodulated value is called as deviation, represented as delta. The deviation is proportional to the instantaneous voltage of the modulating signal. The modulating signal is given as xt equals Em cos 2 pi Fm into t. The carrier signal is given as Ec equals A into cos omega c into t plus phi. The instantaneous frequency of a Fm wave is given as Fit equals Fc plus Kf into xt. Substituting the value of xt, we get the equation Fit equals Fc plus delta into cos 2 pi Fm into t, where delta is the deviation. Minimum frequency of the modulated wave is given as F minimum equals Fc minus delta, and maximum frequency is given as F maximum equals Fc plus delta. The bandwidth of FM wave is calculated as Bw equals 2 into number of sidebands. It can also be obtained using Carson's rules as Bw equals 2 into maximum deviation plus maximum frequency. Consider an example now. In a FM system, if the maximum value of deviation is 90 kHz and the maximum modulating frequency is 15 kHz, then calculate the deviation ratio and bandwidth of the system using Carson's rule. we have maximum deviation equal to 90 kHz and maximum modulation frequency equals 15 kHz. We need to find the deviation ratio and system bandwidth. For that, we use the formulae d equals delta max upon f max and bandwidth equals 2 into max deviation plus max frequency. The formula for max deviation is d equals delta max upon f max. Substituting the values, we get d equals 6 kHz. According to Carson's rule, bandwidth equals 2 into max deviation plus max frequency. Substituting the values, we get bandwidth equals 210 kHz. Now let's study FM transmitter. FM also uses the crystal oscillator to generate the carrier signal. This carrier is then applied to a phase modulator. The modulating signal is applied to the audio equalizer, which is basically an integrator. The output of an equalizer is applied to the audio amplifier. Phase modulator accepts the carrier and the modulating signal and produces the frequency modulated signal at the output. The carrier frequency and modulating index are then raised by passing it through frequency multipliers. The carrier frequency is then raised by using a mixer, and then FC and MF are raised to a required high level. The FM signal is then passed through a Class C amplifier to raise its power. The advantages and disadvantages and applications of frequency modulation are as follows. Advantages of frequency modulation: improved noise immunity. Entire transmitted signal is useful. Covers larger area with the same amount of transmitted power. Transmitted power remains constant. Disadvantages: very large bandwidth is required. FM transmitters and receivers are very complex. Application of FM: radio broadcasting such as Vivid Bharati, Radio Mirchi, etc. Sound broadcasting and TV, satellite communication.
Seriously, pay attention. This is important.
Next, we will study about a very important concept: superheterodyne receiver. The process of mixing two signals having different frequencies to produce a new frequency is called as heterodyning. The superheterodyne receiver converts every selected RF signal into a fixed lower frequency called as intermediate frequency. The block diagram of a superheterodyne AM receiver is as shown. Let us see the function of each block in detail. Receiving antenna. The AM signal transmitted in the form of electromagnetic waves. When received, it induces a small voltage in the receiving antenna. RF stage. RF stage is an amplifier which selects the required signal and rejects all other received signals. It also reduces the effect of noise. As its output, we obtain the desired frequency signal, say Fs. Mixer. Mixer receives two inputs, one from RF amplifier and one from local oscillator, satisfying the conditions Fo is always greater than Fs. The mixer mixes these two signals and generates the signal having different frequencies such as Fs, Fo, Fo plus Fs, and Fo minus Fs. Intermediate frequency, IF. Out of the four frequencies produced by a mixer, the difference component Fo minus Fs is selected and all others are rejected. The difference component is called as the intermediate frequency. This IF signal is then amplified and it provides most of the gain to the receiver. Hence, the sensitivity and selectivity of a receiver do not change with the change in incoming frequency. Detector. The amplified IF signal is detected by the detector to recover the original modulating signal. This signal is then applied to the loudspeaker. Automatic gain control. We know that every amplifier has its own gain. Higher the gain, better is the amplification. AGC circuit controls the gains of RF and IF. This keeps the level of the output voltage constant even if the input signal at the receiving antenna fluctuates. The advantages of superheterodyning are no variation in the bandwidth, high sensitivity and selectivity, high adjacent channel rejection. We will see the superheterodyne FM receiver. The block diagram of a FM receiver is as shown. RF amplifier. RF amplifier is used in FM receivers to improve signal to noise ratio of a signal. Also, it matches the receiver input impedance with the antenna impedance, which is required for good reception of a signal. Mixer. Similar to AM receivers, the mixer stage in FM receiver down converts the received signal to the intermediate frequency IF. It is carried out in a similar way as that of AM receiver. IF amplifier. IF amplifier performs the same operation of applying the intermediate frequency to the desired level, but as compared to AM, the FM requires high bandwidth. Hence, IF is nearly 10.7 and BW is equal to 200 kHz. Amplitude limiter stage. In FM, the amplitude of a modulated wave remains constant ideally, but practically, when the wave is transmitted, random, noise and other unwanted signals get added to the modulated signal and its amplitude changes. These amplitude changes must be eliminated before the signal goes for demodulation to recover back the original signal as it is. Amplitude limiter removes all these unwanted signals and hence it is always placed before the FM detector as shown. FM detector. FM detector demodulates the FM wave and extracts the information signal, passing it via a power amplifier. It is then amplified to the loudspeaker. Phase modulation is very similar to frequency modulation. Only difference is that in phase modulation, the phase of the carrier signal changes with the change in the amplitude of a baseband signal. Let's have a quick review of what we have learned in this lecture. The process of varying the amplitude, frequency, and phase of a signal is called as modulation. It is divided into two main types, as analog modulation and digital modulation. They are further divided as AM, FM, and PM, and PAM, PWM, and PCM. Amplitude modulation is the process of changing the amplitude of the high frequency carrier signal with respect to the instantaneous value of the modulating signal, keeping the frequency and the phase of the carrier signal constant. Amplitude modulated waveforms look as shown. Mathematical representation of AM wave is: in this equation, first term is the carrier signal, second term is the upper side band, and the third term is the lower side band. Thus, the frequency spectrum of the AM wave is as shown. Frequency modulation is the process of changing the frequency of the carrier signal with respect to the instantaneous value of the modulating signal, keeping the amplitude and the phase of the carrier signal constant. Frequency modulated wave looks as shown. Mathematically, FM wave is represented as: the frequency spectrum of FM wave is as shown. Lastly, we studied superheterodyne receiver, the process of mixing two signals having different frequencies to produce a new frequency is called heterodyning. Lastly, we studied superheterodyne AM receiver and superheterodyne FM receiver.